I think it's ready. So
we are all here, Sarita. I think Durgesh is
Yeah,
there,
so
Indulekha is
just-
there, Mashumi is there, and
Yeah.
yeah.
I'll just say good afternoon. Welcome to this thesis session. It's a very tight session. I request all the presenters to stick to the time schedule of 10 plus 2 minutes and strictly because we have a number of them. So with that, without too much ado, I will ask Amit Kumar Mandal to share his screen and begin.
Can you see my screen?
We can see your screen, but please make it full screen, presentation mode.
Okay. Okay. Is it fine now?
Yes.
Okay. So, good afternoon. I am Amit Kumar Mondal, currently a postdoctoral researcher at Seoul National University in Republic of Korea. So the title of my thesis is eco-mapping of active galactic nuclei under the supervision of Dr. Blazars Matthew from Christ University and Professor C.S. Stalin from Indian Institute of Astrophysics. Sorry. It's not changing.
Have you shared the full screen?
Yes, I shared. Why it is not changing?
Can you please unshare and start again? Maybe it will.
Yes. Okay, sorry for the inconvenience. Okay, so this is the cartoon diagram of active galactic nucleus and the sizes of different regions of the central parts of active galactic nucleus are mentioned here. And from this size measurement, it is clear that the central part of active galactic nucleus is very compact. So naturally, the question is, can the central region of region be resolved? So the angular resolution required is sub-microsecond to sub-millisecond. So it is really difficult to resolve these regions using any current imaging techniques. Even using the highest angular resolution offered by VLBI, we will not be able to image the BLR of size ranges between 0.01 to 0.1 parsec or torus of size ranges between 0.01 to less than 1 parsec. But there are very few near infrared interferometric observations were done to probe these regions, like gravity collaboration in 2018 and 2019 partially resolved the dust torus of 8 type 1 bright AGN and BLR in 3273. But these kind of observations are limited to very nearby bright AGN. So if there is difficulties with direct imaging technique, then there is an indirect way to probe these regions that is called the reverberation mapping or eco mapping technique. So this method uses an intrinsic property of AGN, that is the flux variability property. So reverberation mapping is based on the response of the emission line from the BLR region or the NR flux from the torus region to the optical or ultraviolet ionizing continuum coming from the accretion disk. So if we can find the lag between these two responses, which is denoted by delta t, and if we multiply the lag by the velocity of light, then that will give you the size of those emitting regions. So the assumptions of reverberation mapping are, the first assumption is the continuum originates in a single central source, so that flux varies as 1 by r square. Light travel time is the most important time scale here. We are assuming that BLR or dust torus responds instantaneously to changes in the continuum flux. There is a simple, though not necessarily linear relationship between the observed continuum and the ionizing continuum. And the main applications are to constrain the size of the BLR using spectroscopic and photometric observations, and to find the mass of the black hole, which can be obtained using this equation, where FBLR is called the virial factor or the scale factor, which is used to convert the BLR size and the observed velocity width into black hole mass. Here the major uncertainty is in the scale factor FBLR, and to constrain the size of the torus. So motivation, the main motivation of my thesis is to find the mass of the black hole and the radius of the inner edge of the dust torus in a large sample of AGN spanning a large range in redshift and luminosity. And to achieve this, we started a long-term new program at the Himalayan Chandra telescope called REMAP, that is reverberation mapping of AGN program. And as part of REMAP in this thesis, we focused on BLR reverberation on MRK 590 to find the extent of the BLR and the mass of the black hole using photometry and spectroscopy. Dust reverberation mapping on 80507 plus 164 and Z22915 to find the inner extent of the dusty torus using optical and IR monitoring. To characterize the BLR of 57 AGN by modeling their light curves taken from different literature, and we did pre-selecting variable quasars for future reverberation mapping observations. So observations reduction analysis. The details of the observations for BLR reverberation mapping and dust reverberation program are mentioned in this table. So for BLR reverberation mapping, we obtained a single epoch spectrum from the 8.2 meter Subaru telescope, and the photometric observations were carried out using prompt 8, a 60 centimeter robotic telescope in optical BR and narrow H alpha Nesto filter. And the monitoring period and the number of epochs are also mentioned in this table. And for dust reverberation program, we used 2 meter Himalayan Chandra telescope in optical BV and NIGH case band. For BLR modeling, data were retrieved from different literature, and for finding variable quasars for future reverberation mapping studies, data from different quasar surveys and Gaia data were used. For reduction and analysis, standard techniques were followed. So this is the Subaru spectrum of MRK 590, where the transfer functions of different filters are also overplotted in this image. So results on MRK 590. So after correcting for the host contamination and the accretion disk contamination, finally we generated the light curves of MRK 590 in optical B, R, and H alpha line light curves, which are shown in this figure. And then to find the lag between the B band continuum and the H alpha line light curves, we used cost correlation function analysis, which is shown in this figure, and we found a lag of 22 days. Then the lag obtained using different methods are also mentioned in this table. Then we plotted our obtained lag in the known lag luminosity plane, which is shown in this figure, where the red star represents our object MRK 590, which lies close to the best fit line. So using this obtained BLR size and the FWHM of H alpha line from the single epoch spectrum, we estimated the mass of the black hole of MRK 590, which is found to be 1.96 into 10 to the power 8 solar mass. So this is the first time measurement of BLR size of 21.44 days, equivalent to 0.018 parsec, and a black hole mass in MRK 590 based on H alpha line. Now come to dust reverberation mapping on 80507 plus 164 and Z22915. So the contamination, the accretion disk contamination in the observed NR flux can be removed using the power law spectrum of accretion disk, which is given by this equation, where the spectral index alpha can be obtained between the observations between B and V band. So after correcting for the host contamination and the accretion disk contamination, finally we generated the light curve in optical and different NR bands. So this is the light curve of 80507 plus 164 in optical V and NIGH case band. And this is the final light curve for Z22915 in optical BV and NIGH case band. So then to find the lag between the optical and different NR bands, we use cost correlation function analysis. So this is the cost correlation function analysis between V and K band for 80507 plus 164. And this is the cost correlation function between V and K band of Z22915. Then we plotted our obtained lags in the known lag luminosity plane, which is shown in this figure, where the colored points represent our object, which also lie close to the best fit line. So using the lag between V and K band as the inner radius of the dust torus, we found the inner edge of the dust torus for 80507 plus 164 to be 35.2 days, equivalent to 0.03 parsec, and for Z22915, 21.9 days, equivalent to 0.02 parsec. So both are the first time measurements. So now come to estimation of the structure and kinematics of the broadline region using Bayesian statistics. So in the previous reverberation mapping studies, people normally used a constant FBLR to find the mass of the black hole, and also they assumed that emission lines respond linearly to the ionizing continuum. But this is not true always. So these issues can be verified using a theoretical model together with observed reverberation mapping data. So for that, we used PBMap code, which was developed by Lee et al. In 2013, and we applied this code to a total of 57 sources for which reverberation mapping data are available in the literature. So the model assumptions are BLR has a disk-like structure. There is a strong correlation between the ultraviolet ionizing continuum and the optical continuum at 5,100 angstrom. And a point-like ionizing source is producing isotopic radiation so that flux varies as 1 by r square, and all BLR clouds have same size and density. Methodology. So first we generated theoretical continuum and line light curves using PBMap. Then we constrain different parameters like BLR size, inclination angle, opening angle, etc. using Bayesian statistics. Then finally, we compared our derived BLR sizes with what is known from the reverberation mapping observations. So I'm showing you one.
You have 2 minutes.
Okay, so I am showing you one result obtained from the PBMap code for the object J1407 plus 537. So the top pane represents the continuum light curve, whereas the bottom pane represents the line light curve. The points with error bars represent the observed light curve, whereas the solid line represents the model recovered light curve, and the right panel represents the model recovered transfer function. This model also assumes that line responds non-linearly to the ionizing continuum, which is denoted by the nonlinearity parameter gamma, and we found gamma to be non-zero for different lines. Insights from PBMap code. So we also checked the RL relation using the results obtained from the model and using this equation, and we found the exponent alpha to be 0.58, which is similar to the value 0.55 obtained from the previous analysis by Lee et al. In 2013. We also estimated the black hole mass using this equation, where FBLR is obtained using this equation, and we found our estimated FBLR ranges from 0.79 to 4.94, and also it differs from object to object. So the estimated BLR sizes using our approach are in general consistent with that calculated from the conventional CCF analysis. The best fitted model H beta BLR size is found to be correlated with the optical luminosity at 5,100 angstrom with a slope 0.58, which is also similar to the value known in the literature. We found the line to respond in a nonlinear way to continuum variations, whereas reverberation mapping assumes BLR to respond linearly. We found a wide range of the virial factor FBLR. So now come to my last work, that is the quasar catalog for the astrometric calibration of the International Liquid Telescope. So for future reverberation mapping program, it is ideal to choose AGN that are known to be variable. For that, we decided to use the field covered by the ILMT, because ILMT will scan those sources frequently so that their variability properties can be studied. The sources that selected can also be used for future reverberation mapping observations using Indian facilities, and the quasars that selected can also be used for astrometric calibration of the ILMT fields, because quasars have negligible proper motion. So for that, we use data from Milliquas catalog and the Gaia 2 catalog, and finally we arrived at a final sample of 6,738 quasars available in the ILMT stripe, which is defined by this declination range. And this is the distribution of the ILMT quasars in the galactic coordinate system. And the main application of this proposed quasar catalog is to do the astrometric calibration of the ILMT field. For that, we performed a simulation, and from our, which is shown in this figure. And from our simulation, we found that we can achieve an astrometric accuracy of better than 0.1 arcsecond using our proposed catalog. So now come to the summary. So for the first time, we found lag between the continuum and H alpha line of 21.44 days in MRK 590 using photometric monitoring. Using this lag along with the Subaru spectrum, we found a black hole mass of 1.96 into 10 to the power 8 solar mass. For 80507 plus 164 and J22915, using optical and infrared monitoring observations, we found the NRH of the dust storage to be 0.029 and 0.019 parsec respectively. These are the first time measurements for these sources. We also disfavor the use of constant spectral index alpha to correct for the accretion disk contamination in the observed inner fluxes in dust reverberation mapping study. From modeling of reverberation mapping data for about 57 quasars, we found the line response non-linearly to the continuum variations, and the scale factor covers a wide range from 0.79 to 4.94. We arrived at a new catalog of 6,738 quasars in the ILMT field of view. They can be used as astrometric calibration to convert the ILMT images to the world coordinate system. They can also be used to study variability and for future reverberation mapping studies. So this is the list of publication during my PhD. So thank you, and a special thanks to Professor Ramsagar and Dr. Shubhendra Rakshit for mentoring and helping me during my PhD.
Thank you, Amit. Now, the judges, please.
So a very quick question. It's a very interesting talk, Amit. I just wanted to know that for your Bayesian analysis, how did you constrain your priors? Did you use uninformed priors, or did you put some constraints on the priors?
Yeah, so we usually use the logarithmic priors, and then we undergone into Markov-Chain Monte Carlo simulation, and from that simulation we estimated the statistical properties of those parameters.
So did you take any guide from the already available data to constrain your prior? The limits of your prior? How did you work out the limits?
Yes. So we used the parameters, the available parameters which are available in the regression mapping studies, like the black hole mass and the velar size as prior. Then, yeah, we feed them in the model.
Okay, thank you.
So, are there more questions from the judges? I don't see any raised hands. In that case, probably we can go ahead. The next thesis presentation is by Raghubar Singh, who will be talking about understanding of lithium production. Amit, you may please unshare.
Yes.
Hello, myself Raghubar. I'm going to talk about understanding of lithium production and its evolution in world star. I did my PhD at IA under supervision of Professor B. Surajit. Here is the outline of my talk. First, I will briefly introduce about the lithium in the evolved stars and unsolved issues regarding lithium legends. Then I will explain about data sources and methodology, and then I will describe results, and I will conclude my talk with summary and future plans. So lithium is first synthesized during the Big Bang nucleosynthesis. And during the course of evolution of universe, lithium abundance has increased to 3.3 days from initial abundance of 2.2 or 2.7 days. This increment is mainly attributed to various sources like the cosmic ray spallation reactions and AGB star, novae, supernovae, or RGB star. So for a main sequence star of solar metallicity, the initial lithium abundance is around 3.3 days. When a star evolves from main sequence to the RGB phase, surface composition of the star changes. This is mainly caused by the first stage. Now, because of this change, lithium abundance depletes. Depending on the mass of the star, lithium abundance reduces to 1.5 or 1.8x from initial abundance of 3.3 days. But still we see there are stars in the RGB phase with abundance more than 1.5 or 1.8x. These are the stars which are called the lithium rich giants. Like in this region, we can see it here. Now, to make more sense of these stars, we can see the SR diagram. Like these stars are located in a very small region. So, and that region is overlapped by two completely different evolution phases. One is the ascending RGB phase, another one is red clump phase. Their physical parameters are almost similar, and the difference is very small. There, if you compare with the observed data, the difference comes in comparable to the errors in the observed parameter of log G, luminosity, or effective temperature. But their inner structure is completely different. So we don't know their first thing. Because of this, their evolution phase is not well known, whether they are ascending RGB or red clump. And like when the star evolves, other parameters like the carbon astro ratio or rotational velocity also change. we see there is no correlation between among them also. So now we know that the lithium-rich giants exist, but their evolution phase is unknown. Also, at what phase of the evolution the lithium synthesis is happening, that is also not known. If there is a lithium synthesis, then how long the star remains a lithium enriched, that is also unknown. And if lithium enrichment has any relation with other parameters like the mass or metallicity. So the major hindrance in this subject are mainly caused by the small sample size. To address these issues, we have used the recently released, we need the data for getting the abundance. We can get the spectroscopic data, and to get their evolution phase, we can use the data of Gaia and the astroseismic data from Kepler. So for spectroscopic data, we use the data from the LAMOS, SCT-HESP, and archival data of Ojha, Gemini, and Subaru. We select our first sample came from the LAMOS data. LAMOS is a low resolution spectroscopic survey. A small region of the LAMOS sky is covered by the Kepler. So now, once we have the spectra from LAMOS, we did for some of the star, we did a follow-up study from SCT-HESP. We analyzed the spectra to get the stellar parameters, T effective, log G, and metallicity. Once we have the stellar parameters, we can get the abundances and carbon isotopic ratio. For this work, we use the radiative transfer code MOVE and model atmosphere of cruise. Now we know the abundances of stars. To get their evolution phase, we did the astroseismic analysis. Astroseismology is the understanding of inner structure of a star based on their observed frequencies. Now we see here that in the power spectra of red giant, we see the radial modes as well as the dipole modes. Now the relation between the separation between two successive radial modes depends on the sound speed, and the period separation between two successive dipole modes depend on the density of the star. When the star evolves from main sequence towards the RGB phase, these two parameters, meaning the sound speed as well as the core density changes. So in this diagram, we can see how this is changing. So this period separation in the RGB phase and in the red chrome phase is totally different. The separation between the period separation is in the RGB phase, this period separation is less than 100. In the red chrome phase, this period separation is more than 150. So we can use this method in our work to separate the RGB star from red chrome star. Now in our sample of star, we know the spectroscopic abundances as well as their evolution phase based on astroseism. What we found first is that in this star, these are around 600 RGB star, 600 RC star. In the RGB star, the lithium line, this is a lithium resonance line. The strength of lithium line in the RGB star is very weak. In the RC star, the strength is varying. And if we measure the abundances by synthesis method, we see that the maximum abundance comes in the RGB around 1.65. That is well within the value predicted by the standard model. But in RC, the abundance changes. So first result which we got from here is none of the RGB star is lithium rich. Lithium enhancement is specific to the red clump star. Now, these are the total sample. In this diagram, we see that these are stars for which we could measure the lithium abundance. They are located in a small region, but if you see their evolution phase based on seismology, these all are the red clump stars. And like I showed that not all the stars in the Kepler field. So the stars for which are not in the Kepler field, we can get their evolution phase based on C by N. In this by C by N method also, we found that all the stars are red clump stars. Now we know that all the lithium-rich stars are red clump stars, but at what phase? Like in the lithium, like the red clump phase itself, or the helium plus phase, is the lithium synthesis happening? Like in 2011, Mokak et al. Found in their simulation that lithium can be synthesized during the helium plus, and like when the helium plus happens, we don't see any observable signature in the surface, but the inner structure can change. Because of the change in the inner structure, that can appear in the astroseismic variables like the period spacing, delta nu and nu maximum. So if you can compare the astroseismic parameter of lithium-rich giants with the lithium normal star, we can say something about at which phase the lithium enhancement is happening. So what we found here, we got a sample of around 59 stars for which we have the spectral parameter as well as the astroseismic parameter. What we found here is that super lithium rich star for which the lithium enhancement has happened recently has a low value of period spacing in comparison to the lithium normal star. And there is a decline from the super lithium to lithium normal phase. So whether this correlation, and there are other parameters also like period, like the frequency separation and maximum frequency, those are also systematically lower for the super lithium star in comparison to lithium normal. So whether this signal, this correlation is real or it is coming because of the different mass and metallicity of star, to see that we found the mass from the astroseismic variables and metallicity from spectra. We see that in all the groups, their mass and metallicity is almost similar, and there is no correlation with mass and metallicity of the lithium. So now we made the models of the helium plus, how the astroseismic parameter post helium plus are changing. And we see that the main plus is followed by the subsequent subpluses. When we compare our data with the models, what we found is that either this subplus 4 or very early RC phase, this lithium.
2 minutes more.
Okay. Either at the subplus 4 phase or the very early RC phase, this lithium enhancement is happening. Because of this limited data set, we could not separate these two phases. So in the summary, I will say that these lithium-rich giants are distributed in all the components of Milky Way, and lithium enhancement is specific to the red current phase, and not a single RGB star is lithium-rich star. And lithium enhancement exactly happening during either at the subplus phase or the very early RC phase. This total lithium enhancement and depletion phenomena is limited within the 2 megayear post helium plus, and subplus phase, the star remains super lithium rich around 0.3 to 0.5 megayears. And in the near future, we want to increase the sample size to better constrain this relation, also to find the physical mechanism which actually causing the excess lithium in the surface. Okay, thank you.
Thank you. Yeah, so Durgesh, maybe you can go ahead and ask the question.
Yeah, hi Raghubar. So nice talk. Can you just go back to your last slide, the one before this one?
Yes.
Yeah, no, yeah, this one. So you say that you are going to increase the sample size to better constrain the period spacing lithium relation. What would you learn in terms of stellar evolution from that?
Okay, based on the already known thing, we don't have any idea of the helium plus. Also, no model suggests anything about the lithium production post in the RGB phase, in the low mass RGB phase. So by this work, we can say that lithium can be synthesized during the RGB phase, particularly at the helium plus. So helium plus is related to the, somewhere helium plus is related to the lithium enhancement.
So you mean to say that you're indirectly going to observe helium flares or something like that in some way? Or
okay, like if you see,
that is very transient, right? You won't, I mean, observing helium flares is sort of very transient. You have to be at right place at right time and all that. So would you be able to see something like that along by doing this?
Like if you see here, this main plus remains there for a very short period of time, but the subsequent subclasses are there for a long time in comparison to main. So maybe if you can observe stars where the star remains for longer time, maybe subclasses can be observed.
Mm-hmm. Okay. Okay, thanks.
Can you comment on that first line of your summary, that these stars are present in all components of the Milky Way?
Okay.
What's the significance?
Okay. What I mean here is all components like thin disk, a thick disk, or halo. So the majority of the stars in thick disk. We also found some stars in thick and halo.
Are there any more questions from the judges? Okay, if not, maybe we can thank Raghubar and move on. So the next presentation is by Tushar Mondal. Tushar Mondal, can you please share? Yeah. Yeah, your screen was shared.
Can you see?
Yeah, we can see. Please go ahead.
Okay, so good afternoon, everyone. And my thesis title is Magnetically Arrested Advective Accretion Flows Around Black Hole and their implication to ultraluminous X-ray sources and blazars. And this work is done under the supervision of Professor Banibruth Mukhopadhyay at IISc, and currently I am at ICT's TFL. So before going to that actual application of ULX and blazar, I like to give one basic motivation of what is the magnetically arrested advective accretion flow. So this schematic diagram left hand side is basically telling that the central black hole is sitting here, and that matter from that either from companion star or from interstellar medium, because of its angular momentum, it spiral down to the black hole and form like this type structure. And at the same time, the huge gravitational potential energy of the black hole will convert to heat or radiation, and we sometimes see very powerful collimated jets. And this mechanism can be, this energetic behavior can be easily explained from the first law of thermodynamics, where this matter density or that black hole foods like mass accretion rate is controlling different kind of radiation mechanism. And you can see if we take Lagrangian derivative and we take multiply with rho, so this is basically telling that rate of change of entropy per unit volume. And in steady state, it can be giving that radial advection of entropy. And this is basically termed as advection parameter. And the right hand side is basically telling that change of heat, where Q plus is basically telling that heat dissipation process through magnetic or viscous dissipation. And Q minus is basically telling different kind of radiation mechanism. So these three parameters controlling different kind of accretion process, so which primarily depends on this mass accretion rate, at which rate mass is supplying from the interstellar medium or companion star. So this schematic diagram is basically telling all kind of accretion phenomena, where this m dot is written in unit of Eddington rate, and the left hand side is basically telling what we observe from different kind of accretion disk. So the most famous example is the standard accretion disk model, and I will compare the other model in terms of standard disk model. So what is happening, that matter consists of ion and electron. When the matter density is sufficient in this zone, so ion electron density will be sufficient, and that like ion electron coupling will be also high. So whatever heat will generate in this dissipation process, like viscous or magnetic dissipation, it will easily convert from ion to electron, and electron can easily radiate out that heat. So whatever heat will generate, it will be radiated out. That means that this becomes cool, thin type disk structure, and it can be extended up to innermost stable circular orbit, where this black hole is sitting here. And observationally, we see very high luminosity, and soft state means that X-ray for X-ray binary case, it is like photon energy in the soft state, and the multicolor disk black body we can see from that observation. And the disk temperature can be predicted what's with the black hole mass from that Kepler disk phenomenon. Now, when the matter density is low, or like black hole mass supply is low, the system will be completely different. So what happens, the matter density is low, that means that ion electron coupling will be very small. So whatever heat will generate, ion cannot transfer to electron through Coulomb coupling. So that means heat will be stored in the system, and it will store as an entropy. The advection parameter will start playing role. So in this case, whatever heat will generate, it will heat up the system, and the disk becomes quasi-spherical type structure. And in these cases, we see very powerful collimated jet and strong outflow. Observationally, this is low luminous state, and the hard spectra, that means that photon energy is hard X-ray range, and it is fitted by the power law, and photon index is very low in this case. quiescent state is the extended version of this lower state, which is very, very faint. And we can see also some magnetic field is threading in this kind of structure. But the situation become completely different when the mass accretion rate is very high, order of Eddington unit and more than that. So we can expect whatever heat will generate, it can easily transfer to electron, and it can be again the similar type of standard days. But the situation become complicated because of high density, photon cannot come out, and it happens the radiation trap is happening, which is known as in the slim disk model. So we can expect very large outflow in this case also, but it will be mixture of these two states like black body, also power law type feeding, and it is known as very high state or steep power law type state. And in this state, photon index is very high for power law case compared to this lower state. So whatever we summarize is given in the left-hand side, but the situation can be complicated. Like it can be mixture of like Q advection and Q minus also start playing a role, and it can be like Capillary flow can be submerging between the subcapillary flow. It's known as two-component advective flow, and for general advective flow, both Q minus and Q advective play the similar role. But the natures become a little bit different, which thinks that the conventional picture may be changed. So one such example is that ultraluminous X-ray sources, which luminosity is very large, and it's like point-like sources. So luminosity can vary 10 to the 39 to 10 to the 41 hours per second. To explain this large luminosity, we can very similar. We can think that either black hole mass can be higher, which is known as intermediate mass black hole scenario, but it is accreting in the sub-Eddington rate, or that mass accretion rate or mass supply that black hole food can be high, so which is known as super Eddington accretion phenomenon, as it happening in slim disk model, or it can be beamed emission. So what is happening, we are observing that is not actually intrinsic luminosity. So to explain this large luminosity, first initially it's come down that apart from that large luminosity, the disk temperature is cooled down, and as we know from standard thin disk model, temperature is directly linked to black hole mass through this phenomena. And if we know the temperature, we can predict the black hole mass. And first Miller introduced the intermediate mass black hole scenario based on this model, and which is explained this cold disk model. Basically, you can see that black hole mass is required around 1000 solar mass, which is known as intermediate mass black hole, can explain the large luminosity as well as the cold disk model. But after the discovery, then this model has been disputed extensively. That hot disk model is basically telling that this is not only pure thin disk model, there are some power law, and if you feed that power law along with black body, this temperature is shifted to this zone, and then it is explained through the stellar mass black hole, but super Eddington accretion phenomena. Also, the cool disk temperature can be well explained through the disk corona coupling model, where the hot corona will extract the heat from the disk and the disk will cool down. So in this way, the super Eddington accretion phenomenon is well established for the ULX cases, but there are much more complicated scenario when these sources, so these are very rare sources, like out of 300 sources, there are only 10 sources with photon index is very low, which is varying 1.4 to 1.8, which is in hard state, but luminosity is very high. So this phenomena cannot be explained through super Eddington accretion. Also, keeping this photon index fixed, the luminosity is varying at least one order of from this value. So we need some alternate mechanism to explain these sources where super Eddington accretion is not applicable. So to come out in this picture, so we can see this hard state mean we have to predict in this zone. At the same time, luminosity is in this zone. That means this nomenclature has to be changed, like bright hard state type spectra. So my thesis work is mostly in this zone where we solve self-consistently the magnetic field equation along with that hydrodynamic, and we try to predict this ULX luminosity and also the blazar classes we see powerful jet. So before going to that exact result, first we quickly show that the model equation, so which is basically nothing but a conjecture equation of mass, momentum, and energy. So the mass continuity equation is basically telling this radius mass flux and the vertical mass flux, and momentum equation is basically telling this advection parameter. This F is basically telling the force associated with pseudo-Newton gravity of that black hole. And this is pressure gradient. Magnetic field has dual role. One is pressure gradient, other is magnetic tension type term. And this W is basically telling that low turbulent field or the small scale field apart from this large scale field, which is parameterized through the separation of alpha parameter. And the energy equation basically telling that ion and electron equation, because this is optically thin medium. So this is left hand side basically TDS. As we so the first law of thermodynamics, Q plus mean that whatever heat will generate through viscous dissipation process, it will goes to ion. Ion will transfer that heat to electron through this Coulomb coupling, and then electron is responsible through this radiation mechanism of Q minus, which is basically taking care of all kind of cooling processes. Since we are solving that immediate equations, we have to take care about no magnetic monopole condition and along with the magnetic induction equation. So solving this 10 coupled differential equation in steady state axisymmetric flow, where the vertical thickness of the disk is getting care from the vertical momentum balance equation. And the boundary condition is basically black hole nature is transonic nature. That means matter velocity is subsonic, far away from the black hole. And near the black hole, it attains the light velocity. So in between, it has to pass some critical point or sonic location, which is known as the sonic point, or at which point the velocity gradient, the numerator with denominator, the denominator will vanish. To get the smooth solution, numerator also has to vanish. And in this way, we can predict that another boundary which will connect the outer boundary to inner boundary through the sonic or critical point location. At this critical point, we can see that how much with the velocity for different component, and we can set what should be the magnetic field strength and geometry. This F is basically telling that inverse of the magnetic field strength, and you can see where the magnetic field is very weak at this zone, then that matter velocity and sound speed is exactly matching. That means Mach number is 1. So that's why the name is sonic. It's came here. As long as we increase the magnetic field, you can see that after that some point the sound speeds fall down, and after this region we did not get any accretion type solution. This is because of the existence of saddle type point, which come from the analogy of damped harmonic motion oscillator solution, which predict this similar kind of equation where the velocity versus r plane, we can see different kind of solution like center type, spiral type, saddle type, or nodal type point. So depending on the slope or the deviation gradient, it can be either imaginary or real, depending on the value parameter. And we can get these 4 different solutions. Since the damping...
Tushar, you have 2 minutes.
Okay, thank you. So for accretion, we have to get the saddle type solution where the accretion solution is much at this point, and we can set this magnetic field strength in this zone. And when the disk becomes toroidal field dominated, then we can see the magnetic barrier is happening. But for the toroidal field dominated case, this matter will slow down near the black hole. To explain the large luminosity, you can see the magnetic field strength when larger than the Eddington luminosity of that magnetic Eddington value of the magnetic field. Then the supply is magnetic field has to be large from the component start. Then it can attain that large luminosity. But for normal conventional advective accretion flow, when the magnetic field strength goes down to this Eddington limit, it cannot explain that large luminosity. So in this case, that magnetic energy can explain where the available energy is around this range, where the gravitational energy is very low compared to that magnetic energy, which can easily explain that value. In the second application case, we have applied for the AGN or blazar classes, which is classified in 2 different blocks. One is FSIQ and the BLI. BLI is further classified depending on the synchrotron peak position, HSP, HSP, or LSP, BLI. So you can see FSIQ luminosity is very large compared to the HSP, BLI. And photon index also very high. That means it has much larger accretion rate compared to that HSP BLI. Other observation is telling that observed luminosity can be linked with intrinsic luminosity, and that intrinsic luminosity is matching with that accretion disk luminosity. So we can calculate that intrinsic luminosity from that observed one. We can compare all these disk phenomena from the disk phenomena on this observed one. So we need for the beaming correction. So where the observed luminosity intrinsic luminosity is corrected through this dotted beaming factor, and this M and N basically telling that which type of jet, continuous or discrete jet, or which type of cooling mechanism, external cooling processes. So depending on that, this observed luminosity is shifted to this intrinsic luminosity for different cases. The first one is for FSRQ, this is for HSP BLI. To broad classes, when you see that observed luminosity is 3 orders larger, the intrinsic luminosity after beaming correction comes to the same order. And the accretion rate for FSRQ is much higher compared to the HSP BLI, and it can be explained with the accretion disk phenomena, where you can see that accretion rate for FSRQ is very high, but the luminosity is low because that HSP BLI has large magnetic field near the jet footprint where the jet launching region is happening. And at the same time, that ISP, LSP come in between, and LSP is very close to the FSRQ BLI. That's why the magnetic field strength is close to in this zone. So this is the summary of my talk. So first is that highly magnetized advective accretion flow provides generic explanation of the unbound matter where the Bernoulli parameter is positive and hence provides strong outflow and jet. For ULX cases, we see that which are on the hard state, not the superintense kind of phenomena, which is magnetically powered advective accretion flow and stellar mass black hole, and no need to incorporate that intermediate mass black hole concept for superintense accretion. And this strong large magnetic field has to be supplied from the component star, otherwise this large luminosity explanation cannot be possible. That's why these sources are very rare. And for HSP BLI, we see that the accretion rate is very low, and it's gradually increasing to ISP, LSP, and FSRQ cases. And to explain the intrinsic gamma ray luminosity and also that spectra, the HSP BLI is large magnetic field compared to that FSRQ. So next future plan is that since we mentioned that ion is heavier than electron, so whatever heat will generate, it ion will take care and then it will supply to electron. But in optically thin medium, electron can directly get some heat from that dissipated process, so which can give the ion energy process how it is happening. And also we supply the large scale magnetic field from external medium, but it can generate from some turbulent dynamo mechanism, and it can give what should be the more prominent mechanism we can compare with the large scale magnetic field. So these are the references. Thank you.
Thank you. May I now request the judges, Moushumi.
I just wanted to know, Tushar, thanks for your talk. I wanted to know whether you completely rule out intermediate mass black holes as ULX origin by your work. Is it completely ruled out?
No, I did not rule out, but the sources we particularly choose where that you can see that luminosity is fluctuating, keeping that photon index is very fixed, like very low stage. That means if it is intermediate mass black hole, then you have to change that accretion rate to explain that large luminosity. So in this case, you cannot apply that intermediate mass black hole as well as super Eddington accretion. So we are particularly targeting in this source. So we are not commenting that intermediate mass black hole exists or not, but in these sources, it is very difficult to explain by considering both the mechanisms.
Okay, thank you. Thanks.
Any more questions from the judges? If not, I think we'll move on. Thank you, Tushar. If you can unshare your screen.
What is the
one question by Indulekha.
At the end, you said you will be looking at large scale fields generated in the flow itself.
Yeah, yes. So what is the question? Large scale field generated through the turbulent process or this dragging through from external medium? Are you asking? Hello?
Indulekha, if you could repeat.
Am I audible? I think the signal.
Yeah, you are audible.
I just wanted to ask about that last sentence you wrote. You were looking at large scale fields which are generated in the flow itself. Where earlier you made the statement that these luminous hard states are rare because appropriate, mass donor stars.
Right. So what we want to mean, whatever I have studied here, we neglect that it is generated locally, rather it is generated externally from component star and through continuous accretion process is dragged inward and become dynamically dominant, which explain that large luminosity and all these phenomena. But it can be possible that in between the local turbulent, local small scale field can give also large scale field. So there should be some competition between locally generated or externally generated. So we want to look next, so which phenomena will be more dominant, and then it will be much better to comment about both this comment actually.
Okay, so thank you, Tushar. We will move on to the next speaker, who is Ekta Sharma, and she has shared the screen. So Ekta, you can make it full screen and begin, please. Ekta, we can't hear you. I don't know if you are speaking. So if you think you will take some time, or can you hear? Yeah, you can hear, but we can't hear you. So probably we can move on to the next speaker while you sort out the audio issues. Okay. All right. So the next speaker is Rakesh. Rakesh, you are around? Rakesh?
Rakesh, you are muted if you're speaking. Unmute yourself, please.
What about Susmita Das? Rakesh, Mazumder, Susmita Das, anybody around?
Headphones connected to her
Three.
device.
Okay.
The right one.
Ekta?
Devices.
Yeah. Ekta, your devices, I think many are connected. Can you just see that there's only one connected? What does it say?
Sarita, Susmita is saying she's there. She needs to be unmuted.
Oh, I see. Make the focus.
Already done.
Okay.
Yeah. Can you, yeah,
yes, I'm here.
Yeah, may I request the organizers to please make all the speakers co-host immediately. Don't wait for the last moment. Can you please do it immediately so that we don't waste this time in transition?
Yes, Susmita, can you please share your screen and begin?
Yes, ma'am. Good afternoon. I am Susmita. The title of my thesis is Light Curve Structure of Variable Stars and its Applications, carried out under the supervision of Professor H.B. Singh. Here is the list of my peer-reviewed publications, and this is the list of my conference proceedings. Before we begin, let me first break down the thesis title. Variable stars are those that change their brightness over detectable periods of time. Light curve is simply the variation of brightness or magnitude with time. As is evident from these two figures, different types of variable stars exhibit totally different light curve structures, and therein lies the importance of studying the light curve structure of variable stars. We begin with the HR diagram showing the various classes of pulsating variables. The objects of interest for this talk are the classical pulsators, that is, the stars lying within the classical instability strip. In particular, the RR Lyrays, the delta Cepheids or the classical Cepheids, and the type 2 Cepheids. One of the most important applications of classical pulsators in stellar astrophysics is the estimation of extragalactic distances. From this figure, we find that the PL relation of Cepheid constitute the first rung of the cosmic distance ladder that can be subsequently used to determine the local Hubble constant. Here are the specific projects and motivation. The broader idea of my thesis was to utilize modern multiband time series data from wide field variability surveys and perform complementary theoretical studies with pulsation models. Coming to the methodology, we first phase the raw light curve, which essentially folds the entire information to exhibit the brightness variation over one cycle. Next, we fit the phase light curve with the Fourier sine series of this form, which is shown in the red line here. The Fourier coefficients AK and phi k are redefined as Fourier parameters. Fourier parameters are extremely important throughout this talk because they quantify the light curve structure. Before proceeding towards the analysis, we also have to correct for the extinction using the following relations. For our first project, we carried out an extensive light curve analysis of RR Lyrays using the most recent models from Marconi 2015 and observations from the Oglethorpe survey, which contains the largest collection of variable star data. We compared the theoretical Fourier parameters with those from observations and found a good consistency between the two, especially in the RR Lyray range, that is, for periods less than 1 day. There is a greater offset in the longer period models that correspond to the type 2 Cepheid region. We also find that the phi 3 parameter matches well with observations over all period ranges. As a direct application, we compared all the models with the light curves of RRAB stars in the LMC. We used the following constraints: that the period and the Fourier coefficients of the models and observations should lie very close to each other. Using these conditions, we found a total of 25 matches and thereby obtained an average distance modulus to the LMC of 18.51, which is in very good agreement with the published result of 18.49. Next, we study the interaction of the hydrogen ionization front and the stellar photosphere, both from the observational as well as the theoretical aspects. For the observational aspect, we study the empirical period color relations. For the theoretical aspect, we computed a few MESA models to determine the distance between the HIF and the stellar photosphere theoretically. We begin with a few definitions. So stellar photosphere is the zone with optical depth 2/3. Hydrogen ionization front is the zone where majority of the hydrogen becomes ionized. PC relations for Cepheids and RRAB stars have been studied for long, and the results have always been consistent. Flat PC at maximum light for long period Cepheids, and flat PC at minimum light for RRAB stars. This can be explained as follows. When the HIF and photosphere are engaged, the temperature and color are same for both the layers. During that situation, color becomes almost independent of the global stellar parameters like period, and thereby we have flat PC relations. Now, RRABs and classical Cepheids exhibit different behavior of PC relations because of their different locations on the HR diagram. PC relations of type 2 Cepheids had not been studied before, but even if before we begin, we would expect W Virginis stars and classical Cepheids to exhibit similar PC relations because of their similar regions on the HR diagram. Here are the PC relations from the RRAB stars. We find flat PC at minimum light in the bulge, LMC and SMC, and sloped PC at maximum light in all the three cases. Shorter period classical Cepheids exhibit sloped PC at both minimum as well as maximum light. For the longer period classical Cepheids, we find flat PC at maximum light, sloped PC at minimum light. Here are the PC relations for the type 2 Cepheids, which we study for the first time. So if we look at our BL-HER stars, we find sloped PC at both minimum and maximum light for the BL-HER stars, which is similar to what we saw with the short period classical Cepheids. For the W Virginis stars, we find flat PC at maximum light, sloped PC at minimum light, which is similar to the result from the long period Cepheids. We can thereby say that the HIF photosphere theory holds true from the observational perspective. We computed a few RLI-ray, BL-HER, and classical Cepheid models using MESA RSP. So before we proceed to determine the distance theoretically, we have to make sure that our models indeed match with the observations. From this figure, we find that there is indeed a very good match between our models and observations with respect to the light curve structure when we study the Fourier parameters. We also find very good match with the observed PC relations. We therefore move forward to theoretically determine the distance between HIF and photosphere, which is displayed in this figure. So these are the theoretical distances between these two zones at minimum and maximum light. Here we see that RR-Lyrae models exhibit engaged HIF and photosphere at both minimum and maximum light. For the long period classical Cepheids, we find that the HIF and photosphere are engaged at maximum light, thereby resulting in the flat PC relation at maximum light. On the other hand, at minimum light, we find that there is a clear disengagement between HIF and photosphere, thereby resulting in the sloped PC at minimum light. BL-HER models and the short period classical Cepheids exhibit somewhat intermediate behavior between the two. Thereby, we can say that the theory also holds true from the theoretical aspect. Moving on to the last project, where we computed a very fine grid of BL-HER stars to study the effect of metallicity and convection parameters on the PL and the PR relations. BL-HER stars are type 2 Cepheids with pulsation periods between 1 and 4 days. They are also very useful distance indicators, but somehow not as extensively studied as RR-Lyraes and classical Cepheids. There have been indications of low metallicity effect, which is the motivation for our current project. We want to theoretically explore if there indeed is low metallicity effect on the PL and PR relations. If found true, this would offer us a huge advantage over RR-Lyraes and classical Cepheids, which are known to have very strong metallicity dependence on the PL relations. We begin with the linear computations over a very fine grid of metallicity, stellar mass, stellar luminosity, and effective temperature. Using the condition that the growth rate should be positive in the fundamental mode, it helps us estimate the red and the blue edges of the instability strip. Because we are going for BL-HER models, we also want to make sure that the pulsation periods lie between 1 and 4 days as shown by the dashed line. So here in this area of intersection lie our objects of interest, which are the BL-HER models. So we proceed with the nonlinear computations for the models lying within this area. So after the nonlinear computations, we have to make sure that the models satisfy the condition of full amplitude stable pulsations. For this, we need to check that the radius, the change in radius from cycle to cycle, the pulsation period in gamma should not vary by more than 0.01 over the last 100 cycles. For this particular case, this the models computed using set A, B, and C satisfy these conditions. However, we find that we have to reject the model computed using set D because it does not satisfy the condition of full amplitude stable pulsation. So we had started with about 20,000 models in each of the convection set, using the conditions that we need to have positive fundamental growth rate, period between 1 and 4 days, and models that satisfy the condition of full amplitude stable pulsation. We are left with about 2,000 to 3,000 models that that are really used in our analysis.
Susmita,
on the right, we show an example of the multiband light curve.
Susmita, 2 minutes you have?
Yes,
you have 2 minutes more?
Yes. Yes, thank you. Here we show the an example of the multiband light curves computed using MESA RSP. So this is the result. This figure shows the period luminosity relations over multiple wavelengths. The different lines, the different colors over here show the different metallicities. From here, we can see that there is a very strong effect of metallicity in the U and B bands, but negligible effect of metallicity on the longer wavelengths. This is also in agreement with earlier empirical results. Coming to the period radius relations, we find that the theoretical slopes computed using our work is in very good agreement with previously published empirical as well as theoretical results. We also check for metallicity using the mathematical form log R is equal to A plus B log P plus C Fe by H. We find weak dependence of PR relations on metallicity. A very interesting result is that we found identical coefficient of metallicity for all the 4 sets of convection. To summarize overall, we had computed, we had carried out a multi-wavelength light curve analysis of RAV stars and found the Fourier parameters to be consistent from both the theoretical and the observations. We had used a subset of 25 stars to obtain distance modulus of LMC to 18.51. We had also studied the HIF stellar photosphere interaction theory from both the observational and the theoretical perspectives. Finally, we computed a very fine grid of BL-HER models using MESA RSP. We found the effect of metallicity on PL relations to be significant in U and B bands and negligible in the infrared, agreement with previously published results, and no significant metallicity effect in the PR relation. Future projects would include multi-band light curve comparison of the computed BL-HER models and also extending our BL-HER project to include RR Lyraes and classical Seyferts. But one of the most interesting projects in the near future would be to compute MESA RSP model in the G band, that is the Gaia band. Because we know that Gaia DR3 promises to provide very accurate parallaxes, which will help us calibrate PL relations. So in the near future, it is very crucial to compute MESA RSP models in the Gaia bands. Finally, to conclude, I would say that it is indeed a very exciting time to be involved with pulsating variables, because on one hand, we have the open source MESA RSP code. On the other, we have several state-of-the-art observations coming in. So I would like to take this opportunity to thank my collaborators. And finally, thank you all for your kind attention.
Thank you, Susmita. So, Rakesh.
Yeah, Susmita, so a lot of work, observational. Just for my own understanding, so if you let's say get a significant relationship between the period and the metallicity,
yes,
what do you learn about? What do you learn in terms of physics about of variable stars? Or most of the work you showed is like, okay, you did a lot of observational correlations and all. but that is something which missed that what actually you learn about these stars. So let's take this example. For example, if you do get significant relation between periods and metallicity, what do you learn about variable stars?
So when we say different metallicity, we so suppose LMC and SMC will have different metallicities, which is why we obtain different the effect of which is why there exists the effect of metallicity on the PL relation, right? So metallicity plays a very significant role because it affects the PL relation. It affects the light curve structure as well. So when we say effect of metallicity, suppose there also exists. So when I say, just a second. Yeah. So metallicity, there also exists a relation between this parameter, phi31 period and metallicity. So depending on the metallicity, we will have different light curve structures. Does this answer your question? But what we are looking for is, so when there is an effect of metallicity, it affects our, when there is an effect, when the effect of metallicity is significant, it inhibits our calibration of the PL relation, which will ultimately help us in estimating the Hubble constant. So for our kind of work, when we are trying to estimate the local Hubble constant, we actually want accurate calibration of the effect of metallicity on the PL relation, or better still, if we manage to find certain types of variable stars which are known to show no metallicity effect, such as the BL Hercules stars.
Okay, thank you.
Yeah. Any more questions? I don't see any raised hands, but okay. So thank you, Susmita. You can unshare your screen. Is Rakesh Mazumder around?
Yeah, am I audible?
Yes, yes. Please share your screen.
Yeah, let me try to do that.
There's a share screen green button below.
Yeah, I'm just doing, just give me a minute.
Okay.
Yeah. So now is it shared?
No. It's happening, not yet come. Yes.
Okay, let me try to go full screen now. Okay, not that one. So I hope now it's full screen as well.
Yes, please go ahead and begin.
Okay, so good afternoon, everybody. So I'm Dr. Rakesh Mazumder, and now I have recently joined as a physics curator at BITM in CSM, and I have done my PhD from CESI, ISR Kolkata, under the guidance of Professor Dibyendu Nundy and Professor Dipankar Banerjee. And after that, I done 2 years of post-PhD research, one in year in Indian astrophysics, and then 1 year, more than a year in ADS. And then just recently, last month, I joined here as a physics curator. So this was my journey for my PhD 5 year, so more than 5 years, so which I'll brief in 15 minutes. So the overview of my talk is will be several projects during my project PhD, but that couldn't be categorized in two broader category. One is aspect is more of seismology of the solar filament, and first two project will be regarding that, and then I'll come to another aspect of solar filament, but this time not the seismology, but rather long-term variation of the solar filaments, different properties of solar filament, and what the physics out of that we have made. So that I'll discuss. So first thing first, what are the solar filaments? So as history goes, these are visible during only the eclipses, and also due to historical reasons, they are also named as a different structure, filament, and prominence as they are seen on this as a dark filament structure, or they're brighter in when they're looked at the limb side, but they're basically the same structure. They're cool chromospheric plasma and then hanged against the gravity in the corona, solar corona, against the gravity with the help of the magnetic tension. And now filaments are a very amazing feature in the solar corona, though a lot of research has been done and they're known very well, but still we do not understand fully how they, few filaments are very stable and can survive months, and few can erupt very quickly, and they are also important for the space weather research due to their eruptive and event and production of the CME due to their eruption. So with this motivation, which I already talked about here, just I mentioned some more, because CME and all this kind of eruptive event which is associated with the filament is very much about a concern in space weather research. But not only that, but from the large scale variation which I'll talk about, it is also important to understand their variation over the solar cycles, and thus will also will be able to tell about the solar magnetic field variation, and we can use the filaments as a proxy of magnetic field, which like for historical data of the magnetic field, direct observation not available, but we can make filament as a proxy of that, and that way also it's help us. So first thing first, let's just go through my first project. So it was a very interesting event. So one filament, you can see it was in the Gong movie, and as well as other AIA SDO channels, but there are some SDO eclipses. During that there was no data, but anyway we had a good event, and you can clearly see two filament dips, and they are oscillating in the both of the polarization, transverse as well as longitudinal polarization, which was quite unique. And then we just place slit, and we just place slit on this. You can see the earlier work on the same event has been done by the Pant et al, and they analyzed the transverse polarization. And we in my work I have done the longitudinal one, and by the sinusoidal and damp sinusoidal fitting we have estimated different filament parameters, and as well as the magnetic field, estimation of the magnetic field in the filament, which is different, very difficult to find otherwise. And due to this, as I told, we are able to only find a few periods in the AIA due to the SDO eclipse during that era. And here I'll skip a bit due to lack of the time, but nevertheless, if someone has question or interest, I later on can come back how exactly we find different parameters of the magnetic structure of the solar filament, or geometrical structure of the solar filament, and then from that how we estimate the lower bound of the magnetic field in the solar filament. And here was our proposal scenario of this interesting simultaneous both polarization of the oscillation present in a single filament, which was for the first time reported in our work. So that was the cartoon picture we have proposed, and motivated from this simple cartoon picture, later on a lot of simulation work has been done, and similar scenario has brought up by the Chen et al and others. So now that was the summary of this project. So for the first time, as I already mentioned, we have found large amplitude longitudinal oscillation. So in short, we call them LAL. So and it was both the polarization and the other result I has just quoted. Due to lack of the time, I'll not read them out. I'll just go to another event, which was again we found this both polarization, but this time very very interestingly, we can even see the threads, individual threads in the filament, which was not done earlier. And also this event was quite unique because before that, if you can look at this event's movies, the second event movie, it was going to erupt, then it's fall back on its equilibrium position, and then it's oscillate on its equilibrium axis. So it was very interesting, and as well as like earlier event, both the polarization can be seen, but very uniquely we can identify the threads. Again, we place the slit to extract the parameter of the oscillation. And you can see that not only this only one slit has been shown, but another slit has it is also been shown to for some time. We have placed the transverse slit as well to catch that polarization of the oscillation. Now this is just to show how we select the region of interest and place several slits to extract information of the different oscillation of the different threads. And then this movie just to illustrate how exactly we do that from, because this is not a spectroscopy, this is just imaging, but from imaging, how do we place the artificial slit and how we stack our intensity maps and how we produces time distance, or so-called XT map. So this is within just an animation of that. I have made that just to show you that. And then this was the result from that work. So you can see, we can see clear signature of oscillation in all the threads. And interestingly, as I quoted, one thread was oscillating in the transverse direction as well. And using both the polarization, now like the earlier event, we can also estimate these different parameters. But interestingly, since which we missed in the last event, we can see the threads and we can estimate both the polarization. We have tried to estimate the length of the filament from these two polarization, and that we have used this Dimova and Ruderman et al. 2005 relation to do that. And this was the first kind of attempt to make such a indirect, but rather much more which you can say more direct, rather than just from the eyes you can estimate the filament length. This is much more rigorous in that way. And then now I'll go to my another part of the thesis, which is the long-term evaluation of the solar filament properties. So first we have exploited the Macintosh database, which was by the great scientist. Hello.
You have 2 minutes more.
2 minutes more. Okay, thank you. Thank you. So since 2 minutes more is left, I'll just wrap up and go a little fast. But if you have any question, please feel free to ask that. So this is Macintosh database. So from that we extract, you can see different feature in that. But since we are interested in the filament, first thing to determine the filaments, and from the simple image processing, we do that using IDL. And then we estimate the tilt angle by fitting straight lines and see the distribution of these filaments position, their centroid, how they are distributed over the latitude, how their distribution of the latitude differs in the time, and how nicely they can produce butterfly diagram, and also migration to pole, how distinct and how clearly they are visible, which is not the case for the solar sunspot, which you can just see up to 45-degree latitude. So like this filament can give much more information about the migration to the pole, which we have also shown that correlated with the polar reversal. And after this kind of report, a lot of work has been done in future motivated by this filament, tracking filament and pull to the migration, and importance has been understood of this kind of filament long-term database. Now also one aspect we exploited is the tilt angle issue. So there are some anomalous tilt angle behavior, which I'll not go into detail due to lack of time, but I'll just say we have found that they are not as we expect the tilt angle distribution. And from that what we have proposed that it is rather the large scale structure which contributed more to the filament formation rather than bipolar small sunspot structure. And this was in this work our definition or determination of how filament are actively associated or not. In my next work, and also I'll just skip few slides about the north-south asymmetry, which is again,
can you wind up now, because you come to the end.
Just give me 15 seconds or 30 seconds.
Okay, sure.
Yeah, so I'll just give the summary and conclusion. In the next work, yeah, we have detected the filament again, but it was the determination of the filament tilt angle, which is we have improved in our next work. And there are other challenges of the detection of filament from the MITO and other database, but that I'll not discuss due to time lag. But yeah, I'll just now wind up with this result and figures of that work. And we use just Plage's positional information to do that better estimation of the filament association of active region. So this was the list of publication which was included in the thesis, and some additional publication which is not included in the thesis and conference proceedings. And I want to thank you, and especially to my supervisors. And if you have any question, you can ask me. Thank you.
So thank you, Rakesh. BCJ.
Yeah, one quick question. You estimated these periodicities and you showed one slide earlier. For lack of time, we'll not go there. My question is, what is the uncertainty on your period estimation?
Yeah, I have measured the
particularly. So just to clarify, particularly because in one of the slides you showed that the number of cycles was only 2 cycles or 3 cycles.
Right. I understand your concern. So we have exactly quoted what are the uncertainties, and due to just data unavailability, whatever best we have can do, we have done it. Yeah,
I understand that. My question is, what is the confidence limit which you have on those uncertainties? Okay.
Yeah, we have quoted the error.
So how did you actually estimate your confidence on those uncertainties?
Yeah, because this is 2 kind of error goes in. So one is the fitting error, which you can go with this 2 or 3 periods, you will get much more uncertainty. And another estimation and detecting those dark points, right? So that is automatically done. We have fitted a Gaussian, and then we do the minimum, select the minimum point. So all that error bar is also included. So, and with whatever the plus minus this kind of 2 is including all the error, you can like.
Okay, so you are saying from the fitting errors alone, right?
No, not fitting error. That's my point. We propagate also not only fitting errors. Fitting errors, that we also consider when we are coming to the final magnetic field value. But also while we are estimating this, all those black points, so we fit a Gaussian. That error also we propagate to the final result, and that we estimate in the parameters like amplitude, periods, like that. But in the final magnetic field calculation, we propagate all this error, whichever parameter goes in that calculation. Yes.
Okay.
Durgesh?
Yeah, Rakesh, I have many questions, but I can't ask all of them. Maybe one quick and then another one. Sure. That these oscillations are damping. So can you comment on the physics of those damping?
Yeah, so we have not only estimated the damping, but this is a quick damping you can see, and the resonant absorption is one more one we speculated about this damping mechanism, and that is discussed in our paper. And
so how actually resonance absorption damps the oscillation?
Sorry,
how exactly does the resonance absorption work in damping these oscillations?
Yeah, so when there is a driver, you start something oscillating. So it's a there could be different mechanism. One could be this your energy, how you're losing your energy. So of your energy driver. So one as could be like conduction, another could be resonant absorption. And we have not done the exact analysis of and tried to determine what goes in what. We have just mentioned those could be possible scenarios, but we have not measured or done any analysis on the reason of the what percentage goes in resonant absorption or what goes in other mechanism. We have just speculated this kind of high damping can be not only due to only conduction, but that there should be resonant absorption to explain such kind of high damping.
Okay, thanks.
Yeah.
Okay, thank you, Rakesh. So if you can unshare the screen.
Hello?
Yes, you are audible.
I'm audible.
There is some noise, but you can reduce that.
Yes. Am I audible now? Clearly? Hello?
Hello? There's a lot of background noise you think. Can you please remove all the headphones?
Yeah, I have done that. I'm just using one, not using any headphones right now.
We will move to another one. You can check and come back.
Okay, sure. Yeah, sure. Thanks.
Please mute. Yeah. So is Tridib Roy around?
Yes.
Okay.
Yes, okay.
So Tridib, can you please unmute and share your screen? If you're speaking, we can't hear you. Can you please say something? I don't know, we can't hear you yet.
Yeah, am I audible right now? Yes. So my screen is visible right now?
Yeah, your desktop is visible. Can you open your top?
Okay.
So if you can share your full screen right now, we can't see. So
Next one. No.
yeah, we can see your screen. Can you please open your presentation and begin? We are already running behind.
Let me see. Wait.
Is your presentation open? Yeah. I think he's sharing his desktop, but
It's not visible.
yeah. So can you share your entire screen? You're sharing screen, but where is your presentation is something we can't see yet. Is it open? Yeah, there's no presentation. Is it open?
Yeah, let me see.
So can we do one thing? Can we come back to you? If Vineet Ojha is around, you can actually figure out.
Presentation is what is this?
Can you please unshare and maybe you can check it out?
Yes, yeah. I am here.
Okay, so Tridib, can you please unshare so that we can go to Vineet Ojha? Meanwhile, you can try to figure out.
Okay, sure.
So Vineet, can you please share your screen?
Okay. He hasn't unshared.
No, it's unshared.
Oh, okay. No.
Okay. No.
Can you see my slide?
Yes. Can you make it full screen and begin?
Okay. So I'm audible and my slide is looking fine?
Yes.
Yes, okay. May I start?
Yes, please.
Okay. Hello, this is Vineet Ojha, going to deliver his thesis talk titled Multi-Wavelength History of Narrow Line Seyfert 1 Galaxy. My thesis talk, outline of my thesis talk is that first I will introduce AGN and its connection with narrow line Seyfert 1 Galaxy. My whole thesis talk is divided into 4 parts, and in each part I will discuss in each part I will discuss a published work of mine. So moving to introduction. So AGN is a compact region in the center of galaxy that emits enormous amount of energy from in all electromagnetic wave band. Initially, AGN are classified into two largest subclass based upon their radio to optical output into radio quiet and radio loud. So although the radio emission can come from the star formation as well as from the corona, but the majority of the radio emission come from the relativistic disk. So therefore, radio quiet objects are thought to be not associated with the disk. So narrow line Seyfert 1 galaxy are initially classified as a radio quiet object, and this is a typical spectra of a narrow line Seyfert 1 galaxy. You can see the narrower H beta line, which is less than 2000 km per second. Flux ratio of O3 by H beta is less than 3, and there is a strong iron emission line present in their spectra. This is a characteristic of narrow line Seyfert 1 galaxy. So as I told that narrow line Seyfert 1 galaxy were initially classified as a radio quiet object. Therefore, they were also thought not to eject jets like those observed in radio loud AGN. So, however, main path break came for this class of AGN after the detection of a few narrow line Seyfert 1 galaxy in gamma ray band by Fermi light, and this strongly suggests the presence of relativistic jet in them. So, this is because the non-jetted object such as blazar, which are gamma ray detected, they are invariably detected in radio band. The optical flux variation from the minute to hour lifetime scale is commonly known as intra-night optical variability, and people use this tracer, use this tool as a tracer of jet activity in other classes of AGN based upon the duty cycle achieved for the non-jetted class of AGN such as blazar. So, so what is duty cycle? Duty cycle is the nothing but it is the fractional time over which an AGN is found to be variable, and this psi is the amplitude of that variability. So the motivation of my first work came from the published article by Sama et al., where they have done the INOV of a different classes of a narrow line Seyfert 1 galaxy, that is gamma ray loud, gamma ray quiet, and radio quiet. So by including 4 objects in each classes. They have found the highest duty cycle of INOV for the gamma ray loud and somewhat lower for the gamma ray quiet, and none of the source variability for the radio quiet. But however, we noted that in his sample, the highest duty cycle shown by the gamma ray loud NLS-Y1 include all the sources to be radio loud, and however somewhat lower duty cycle shown by the gamma ray quiet included only 50% of sources to be radio quiet, radio loud. So at this stage, we have posed a question whether radio loudness parameter is the prime factor to detect the INOV in narrow line Seyfert 1 galaxy, or detection in high energy band such as X-ray and gamma ray have some link with the INOV. So to pursue this objective, we have carefully selected a sample of 18 narrow line Seyfert 1 galaxy which are detected in X-ray but not in gamma ray. And at this time, only 7 gamma ray, 7 narrow line Seyfert were discovered in gamma ray. Therefore, we have took another sample of 7 gamma ray detected narrow line Seyfert 1 galaxy. Since we are interested in inferring the variability of this object, therefore we have used the differential light curve technique to infer that. This is the differential light curve for this sample for two sources. And for checking the variability statistically, we have used standard F test and power enhanced F test. So using the differential light curve and variable statistical test, we have estimated the duty cycle for the X-ray detected narrow line Seyfert galaxy, which consisting of radio quiet and radio loud object, and gamma ray detected narrow line Seyfert galaxy, which consisting of radio loud object only. So but when we subclassified the X-ray detected NLS Y1 into radio quiet and radio light, and we estimated the duty cycle, and when compare their duty cycle, then we have found a comparable duty cycle of radio loud X-ray detected narrow line Seyfert galaxy with gamma ray detected narrow line Seyfert galaxy. So from here we conclude that the energy dependence plays a only minor role, and radio loudness parameter is a prime factor behind the INOV detection. So in this work, we are also able to compare the INOV duty cycle of our work with the duty cycle reported for the other classes of AGN by Goel et al. So we are able to do the same, because Goel et al. Have used the same telescope and same test. So after comparing, we have found the duty cycle of gamma ray detected narrow line Seyfert galaxy compared to the TV blazar. So from here we conclude that in case of gamma ray detected narrow line Seyfert galaxy, the region behind the INOV detection is the relativistic jet magnesium. So furthermore, at the completion of my first work, a few more gamma ray detected narrow line Seyfert galaxy discovered in the gamma ray band, and making it 22. But based upon the multi-wavelength study, people have inferred that the gamma ray NLS Y1 and blazar engender very similar manifestation and property in terms of such as relativistic jets, superluminal motion, optical, violent optical and infrared flux variability. So at this stage, it is very important that searching any contrasting behavior between gamma ray narrow line Seyfert galaxy and blazar class of AGN. So we pursued this objective by selecting a 15 gamma ray NLS Y1 out of 22. These are well selected sample, and used a single telescope, so that instrumental effect does not incorporate here, and done the INOV study of this 15 gamma ray NLS Y1. So we have monitored this 15 gamma ray NLS Y1 in 36 monitoring sessions, and we have also ensured that each narrow line gamma ray NLS Y1 have been observed at least in 2 intra-night sessions. So when we computed the duty cycle based upon both the test, we have found a duty cycle of INOV more than 30%. So which is comparable to the blazar class of AGN. So from here we conclude that even in addition to multi-wavelength property comparable to blazar class of AGN, gamma ray NLS Y1 resembles INOV property similar to blazar class of AGN. And in this work, another contrasting behavior we have found that the out of 15 gamma ray NLS Y1, two prominent members, that is this and this, have shown optical flaring. So which is quite rare for the blazar class of AGN. So we from this result we conclude that flaring activity, optical flaring activity is less rare phenomena in case of gamma ray NLS Y1 compared to blazar class of AGN. So to study the INOV property of narrow line Seyfert galaxy, are a connector of INOV with physical parameter of AGN such as radio loudness parameter, superluminal speed, and polarization. We have selected a sample of gamma ray NLS Y1 for which these parameters have already been measured. So after doing the literature, sir, we have found three such sources, and done the internight optical variability study of these sources by devoting 5 internight sessions to each narrow line Seyfert galaxy. But in this work, we have found the result which is opposite to our expectation. That in first work we have found we have found that radiologinous parameter is the prime factor, but here the source which has the least radiologinous parameter, that is this, has shown frequent INOV in its 5 internight session, and the source which has highest radiologinous parameter and polarization value has shown no INOV in its 5 internight session. So from
minutes more.
Okay. I'm concluding. We searched the region behind this, and when I searched the region behind this, we found that the relativistic jet speed is highest for the source which has shown the frequent INOV. So from this result, we have concluded that the superluminal motion in the radio jet could be the robust diagnosis of INOV. In this study, we have also found a genuine flaring for this source, which is presented here, and for this we have estimated the flux stability time, which is less than 1 hour. So moving to my last work, which is as I already told that as a subclass of AGN, narrow line Seyfert galaxy also emit radiation in all electromagnetic wave band, but their origin of X-ray emission is not well understood. Several authors have given different model for their X-ray emission. For example, X-ray could come from the jet. It can come from the advective dominated accretion flow. It also comes from the accretion flow hot corona system, and well-known model, that is disk corona model. It can also come from the disk corona model. So in order to remove the degeneracy among the aforementioned model responsible for the X-ray emission, a homogeneous analysis of X-ray detected narrow line Seyfert galaxy in conjunction with their optical data is important. So for this, we have prepared a sample of 221 narrow line Seyfert galaxy, and for the comparison, we have also selected a 154 broadline Seyfert galaxy. So for optical X-ray measurement, we have used the data from Rosette and X1 Newton, and for optical measurement, optical physical parameter measurement, we have taken from the SDSS data from the SDSS. After estimating the parameter, that is spectral slope and Eddington ratio, we have plotted the plotted for narrow line Seyfert galaxy and broad line Seyfert galaxy, and we have found a very good correlation in case of narrow line Seyfert galaxy and broad line Seyfert galaxy. But at this stage, we suspect that whether this is continuity and biomodality. But when we jointly plot, then we found that this is continuity rather than biomodality. Another thing, since we have got the correlation coefficient in soft energy band, therefore which is highly which is affected by the soft X-ray axis. But if we find the same correlation coefficient in that energy band which is less affected by the soft X-ray axis, then this would become clear that this correlation coefficient is correct. So when we again plotted and estimated and plotted in that in full energy band 0.3 to 10 kV, we found the same correlation coefficient and a similar trend. So from here we conclude that the X-ray emission mechanism in narrow line Seyfert galaxy and broad line Seyfert galaxy are similar, and as expected from the theoretical prediction of X-ray emission within this corona paradigm. However, we have found a steeper slope of the gamma X, the region behind compared to broad line Seyfert galaxy. So the region behind is that the higher accretion rate for narrow line Seyfert galaxy. So summary of my talk is, in my first work, we have proved we have found that the based upon the high energy detected sample, we have found that the radio loudness parameter is the prime factor, and high energy detection plays a only minor role. But In my second work, we have found that the gamma ray detected narrow line supernovae display blazar-like behavior, except their lower black hole masses and a spiral host. And in my third work, which I have done in deep detail to connect the linkage of INOV in case of narrow line supernova galaxies. So then we have found that the jet speed is the robust parameter rather than radio loudness and energy dependence. In my fourth work, we have found a very good positive correlation between gamma X and RE dictant, and from this result, we conclude that the this corona model follow X-ray. This corona model is responsible for X-ray emission in NLSY1 and BLSY1. So in future work, since in my first work, we have found a similar duty cycle.
We are already. Can you make it?
Just this is lost. Similar duty cycle for X-ray detected radio loud narrow line frequency and gamma ray detected radio loud narrow line frequency. Therefore, a polarimetric check on blazar-like nature of the nuclei is desirable. This work is currently running with the PRL and Aries telescope. And another thing, launching of jet from the gamma ray NLSY1 challenges the theoretical scenario of jet formation, because the jet usually launched in elliptical galaxy. Therefore, a host galaxy imaging is very important to resolve the galactic type in case of gamma ray detector NLSY1. This project is also running with the 3.6 meter Aries telescope. Thank you.
Okay, thank you, Vineet. The judges, do you have any questions?
I think we can move ahead, given that we are running late. Yeah.
Okay, all right. So next we will have Surajit Mondal. If he...
अनशेयर का ऑप्शन नहीं आ रहा है.
Hello. Hello.
Hello.
Can I share my screen now?
What happened? I think. Hello.
Hi. Hello. Yeah. Hi.
Did the IIT Roorkee get disconnected?
I think so. Someone has messaged. The Roorkee got disconnected probably.
Yeah, I can't see Sarita anymore, so I presume that's what the case is. Hello, IIT Roorkee, can you hear us?
Yes, your voice is clear.
Okay, so but
yeah, we are able to hear you. We got disconnected for a moment.
Yeah, sure. So let's go ahead.
Yes, Surajit, if you're around and can share the screen, please begin.
So, can you see my screen now?
Yes, we can. Please go ahead.
Hello, everyone. I will be talking about my thesis, which is titled Studying the Extremes of Solar Activity Using High Dynamic Range, Low Frequency Solar Images. This work was done at NCERT IFR under the supervision of Tridib Roy. Let's start with a brief introduction. The solar corona is highly dynamic, and the coronal dynamics to a large extent is determined by magnetic reconnection processes. During the magnetic reconnection, electrons get accelerated. While this is qualitatively well understood, the exact mechanism, how this acceleration happens, where it happens, and how the accelerated electrons get transported into the heliosphere is still a mystery. Radio observations can provide critical inputs for understanding this problem, as they are very sensitive to non-thermal particles. However, it is known that the radio emissions can vary over small time scales and can have narrow bandwidths. Hence, to use this as a sensitive probe for non-thermal particles, we need to have high dynamic range spectroscopic snapshot imaging in the radio wavelengths. But achieving this is not trivial, because the radio interferometric imaging is a Fourier imaging technique, which means the imaging fidelity is directly dependent on the amount of sampling in the Fourier plane. In case of spectroscopic snapshot imaging, dense Fourier plane sampling can only be obtained by having a large number of antennas. New generation instruments like the Murchison Wide Field Array has 128 antennas, which gives it 8,128 baselines. This gives MWA the capability to sample the Fourier plane in a very dense manner for every time and frequency slice, similar to the figure given here. Now, this huge dense sampling of the Fourier plane gives us the capability to use the MWA data to image the sun at high dynamic range at very small frequency and time slices. However, to address our goal of spectroscopic snapshot imaging at high dynamic range, we also need to address other challenges. For example, how to calibrate the data well. In radio interferometry, generally, all the parameters relevant for calibration can be clubbed together into a quantity called antenna gains. Antenna gains have contribution both from the instrumental response and propagation effects. These antenna gains are generally determined by observing well-modeled astronomical sources or calibrators. In MWA, the calibrator observations are only available when the sun is below the horizon. Now, although MWA instrumental response is quite stable, since the calibrator observations are very separated in time from the solar observation, the propagation effects present during the calibrator observation is very different from that present during the solar observation. Hence, the antenna gains obtained from the calibrator observation can be very different from the true antenna gains during the solar observation. A technique called self-calibration is routinely used in radio interferometry to solve for this difference between the true antenna gains and that derived from the calibrator observation. However, self-calibration is a highly nonlinear and iterative process, and hence it needs a reasonably good starting model for the sky. But this requirement makes it hard to apply this technique for solar imaging in case of MWA, because as I mentioned earlier, the antenna gains which we have access to from the calibrator observations are inaccurate. And using this inaccurate antenna gains, the sky model which we can produce is in general not good enough to start self-calibration. In my thesis, I have developed an algorithm for self-calibration which is tailored for solar imaging purposes with data from arrays which have a centrally condensed core similar to the MWA. This algorithm, along with several other optimizations, have been incorporated into a pipeline which we have named the automated imaging routine for compact arrays for radio sun or AirCars. AirCars has produced the highest dynamic range solar images at similar frequencies and solar conditions. In this figure here, I have shown the highest dynamic range image which AirCars has produced. The dynamic range of this image is of the order of 10 to the power 5. The lowest contour is at 0.02% of the peak, and even at this low level, there is no noise contour in the entire image. This yellow circle here is the optical disk of the sun. Now, we have used AirCars to detect non-thermal particles into unique situations. The first of them is detecting them from the coronal mass ejections or CMEs. These are the most energetic events in the solar system and are a major source of space hazards. Magnetic field of the CME and the non-thermal particles accelerated due to it are a key driver of space weather. However, there are no routine way to measure these using remote sensing techniques. The gyrosynchrotron emission is a very powerful tool to measure both. But this emission has been detected in only a handful of events. It is not known whether this non-detection is due to poor sensitivity, or does most CMEs have weak magnetic fields, or are they inefficient particle accelerators. Using AirCars, we have been successful in detecting gyrosynchrotron emission from a slow and rather unremarkable CME. In this image here, I have overlaid in cyan the radio contours on top of a white light difference image. So this structure which you see here in the background is the coronal mass ejection. And what we see that the radio contours nicely follow the morphology of the white light CME. We have been able to detect this emission till 4.73 solar radius, which is the highest heliocentric distance till which the gyrosynchrotron emission has been detected from a CME. We were able to detect this emission at several frequencies. We used the spectral information to estimate the magnetic field and non-thermal particles. While this has been done earlier as well, since we're able to detect this emission at a much more larger number of frequencies than possible earlier, the parameter estimates obtained here is much more robust than earlier works. In this figure, I have shown the gyrosynchrotron emission measurements of all previous works. And in green, I have shown two example spectrum from this work. It's evident from this figure that the flux densities reported here is the lowest till date. Now, this gives us the confidence that we might be able to detect this emission from CMEs in a regular manner and possibly use these to measure magnetic field and non-thermal particles from CMEs in a routine manner. We've also used AirCars to detect evidence of non-thermal particles from nanoflares. Nanoflares are hypothesized to be ubiquitous small-scale magnetic reconnections which are responsible for maintaining the million Kelvin temperature of the solar corona. Now, a corollary of the nanoflare hypothesis is that, like their larger counterparts, the small-scale magnetic reconnection should also accelerate particles.
Surajit, you have 2 minutes. You have 2 minutes more.
Can interact with the thermal plasma and emit plasma emission. These emissions are coherent in nature and can be detected even in case of weak flares when the thermal signatures can be very weak. Well, this was realized earlier, and hence earlier works have tried to detect these signatures from noise dots. However, the imaging dynamic range was just not sufficient enough to try to detect these emissions from the quiet sun. Using AirCars, we have the ability to image the quiet sun is a much higher dynamic range. In this histogram, I saw the median subtracted and median normalized histogram at different frequencies. The presence of the non-thermal tail is evidence that there is non-thermal emissions present in the data, as this is not expected from a thermal population. Here, I have shown the temporal width distribution from all emissions is present in the power law tail. We find most of these emissions have widths of 0.5 second, which is the instrumental resolution of the data. A necessary condition for these emissions to be the radio counterparts of nanoflares is that these emissions should be ubiquitous. To investigate that, here I have shown a fractional occupancy distribution, which is defined as the fraction of observing time for which these emissions are present on any given patch of the sun. What we find is that these emissions were present in a significant number in every single patch of the sun. Now, let me summarize my thesis work. In my thesis, I have developed AR cards to generate high dynamic range solar radio images in an automated manner with data from arrays with a centrally condensed core. I've applied AR cards to detect the weakest cytosynchron emission from a weak and rather unremarkable CME. This suggests possible use of this technique for regular measurement of magnetic field and non-thermal particles. I've detected the ubiquitous presence of impulsive non-thermal emissions in the quiet solar corona and are probably the radio counterparts of nanoflares. Thus, this thesis has opened up new avenues of exploration in vastly different energy scales, ranging from the high energy flares leading to CMEs and the smallest nanoflares. Thank you.
Thank you, Surajit. That was very much in time.
Are my publications.
Okay.
I cannot go. Next slide. I do not know why.
You can unshare and share. And meanwhile, you can have the questions. Durgesh?
Yeah, hi, Surajit. So nice talk. I have a question. So the radio nanoflares you have been detecting and talking about, how do they correspond to the nanoflares people talk low in the corona in X-rays, for example? Because the height is quite different, I guess, because the frequency range you're looking at. So how do they compare and correspond?
So actually, so what we have been trying to do later is to try to identify if we can find counterparts of these transients in the UV or in the UV actually, and this has been done in only one case where I could find a group of these transients. They were grouped together within about I think 2-3 minutes. There were about 10-20 of these emissions, and the energy scales of that event, which is in the UV, is about 10 to 25 arcs, which just translates to about 24 arcs for every such transient emission in the radio band. Now, at least energetically they match. Other than that, I really, right now, we don't know.
Okay.
Indulekha?
Yeah, you in this last nanoflare work, you were looking at the variability of patches, and I noticed that it is 70 minutes of data and PSF sized patches. Was there any need to account for solar rotation?
Actually, no, because angular resolution for this instrument is several arc minutes. So that is why it was not necessary.
Oh, okay, thank you.
Okay, thank you, Surajit. We'll move on to the next presentation.
Can I try to share?
Yes.
Can you hear me now clearly?
Yeah, it is clear. So please share your screen and begin. Ekta.
Can you see my slides?
Yes. Yes.
Okay, thanks. Yeah, I'm so sorry for the inconvenience. Okay, so I'll start. So hello everyone, I am Ekta Sharma. I am currently a postdoc researcher at PRL, Ahmedabad. So today I will be discussing my thesis work on the investigation of the evolution of galactic dark clouds. So as we all know that the night sky is full of so many bright stars and glittered with so much of light, but there are also blank spaces within that our local galaxy, which we feel like that they are the spaces, they are like the voids, but they look like they are voids and that they are devoid of any gas material, but that is not the case. They appear, so they are nothing but the molecular clouds which appear dark in optical wavelength, but in different wavelengths or in longer wavelengths, they appear brighter. So for the comparison, you can see an example here of the Horsehead Nebula, that in optical, when you see, it looks like a dark structure, whereas when you go to the near infrared range, then you will see more number of stars. And when you go to the far infrared wavelength, then you will see the complete, only the bright the emission from the cloud. So these dark clouds, that's why they are called dark clouds. In optical, they look like dark, and they are basically molecular clouds, and they are made up of hydrogen molecules or other trace gases. So these interstellar cloud, when they fragment, the general scenario of star formation suggests that if they fragment, then that goes on to forming the dense core entities within the interstellar cloud. And then when those dense cores, they collapse under its own self-gravity, then it will collapse to form stars, young stellar objects, or depending on the mechanism, outflow, and then ultimately to form main sequence stars. So my research work, my thesis research work is divided into three parts. One is based on the Cephas flare region. Another one is based on the cloud motion and magnetic fields in the same flare region. And the third one is the magnetic fields in these isolated clouds with asymmetric morphology. So as I mentioned that molecular clouds, they are the stellar nurseries for the formation of stars. They are nothing but the clouds of dust and gas. So if they collapse under their own self-gravity, then the relevant time scale should be the free fall time scale. So all the gas mass available in the Milky Way should be converted to the stars on this time scale, and it should be 200 solar mass per year. But this is not the case. It is just 3 to 4 solar mass per year, and star formation is just 2% from the giant molecular clouds. That means there are other factors in addition to the self-gravity, which are playing role in delaying this overall gravitational collapse. So possible reasons given for this delay were, like, in addition to the self-gravity, could be the turbulence in that cloud structure, or it is being governed by the magnetic field pressure, or the stellar feedback could also play a role in either dispersing or compressing the medium. So overall, the final evolution of the cloud structure may be governed by this in addition to the self-gravity. And then this cloud structure over the last few decades, it's been adopted that through the simulations and the Herschel observation, basically the far infrared detectors, that this cloud structure is highly filamentary. So I'm showing here one example of B211, B213, and these filaments are nothing but having aspect ratio at least greater than or equal to 5. Basically, the length will be higher than the width, and so there are high density filaments categorized with NH2 greater than this number, and then filaments having low density of 8 into 10 to the power 21 are called subcritical filaments. So these filamentary structures, so as it is ubiquitous over the whole ISM, it can have like the active star forming region is also an filamentary, and the one which is not forming stars, just having the fragmented cores like Polaris, that can also have filamentary structures. So when it forms, depending on the way how it is fragmented, it can form these kind of beads along the chain, which are called cores, and then these filaments may be governed by the magnetic field structure. As on the left, you can see that these are the optical vectors, which if they are found to be parallel to the low density striations, but the perpendicular to this high density skeleton. So this kind of study, overall survey, has been done using Herschel filament, total 270 filaments in 8 regions of Gould belt within 400 parsec in Milky Way. And the core mass function in all these clouds was found out to be similar to the initial mass function of stars. And so that suggests that there is evidence for the correlation with stars. So that means these filaments play a central role in the understanding of star formation. That means how these filaments, these structures evolve to cores, that is That is a question worth finding out. But how do the factors like self-gravity, turbulence, and magnetic fields, and also stellar feedback, they kind of interplay to finally decide the evolutionary stage of these these clouds to the dense core is not fully constrained. So I'm interested in studying these physical mechanisms with the use of observations. So these are the telescopes and methods that I've used. So depending on the tracer that I want to look at, magnetic fields, molecular lines, and the emission, I've used this ground-based and archival telescope data. So there is a very interesting arrangement of the filaments in ISM called hub filament morphology, which was first given by Mayers 2009, which suggests that these clouds, basically, they are characterized by the hubs, which contains a massive star of higher gravitational potential with low aspect ratio and high column density. And then there are, so you can see in this figure, then there are the filaments with subcritical masses, basically with low density, which is kind of, so they appear to be like funnels of gas or material which is feeding onto the main cluster. So and where the main cluster formation. So basically, this is a potential site of clustered star formation. More number of ISOs being formed in this morphology. So, but how do these accretion process from these filaments or mass inflow is happening through the hub to the hub through the filaments is happening? That is important to know. So the characterization of these structures are important, and also which factors is playing role, as I mentioned in my last in the previous slide, and what is the velocity structure, so that we can find out whether there is any velocity gradient or not, and what is the dynamics of the cold molecular gas around the massive stars. And finally, I'm interested in looking at what is the origin of these hub filamentary systems. So to do that, I have chosen this Cephas flare region, which is at around relatively higher galactic latitude of around 14 degree. And this is you can see this is a Planck image, a wide variety of filamentary structure. So I've chosen these two clouds to study the molecular line structure and the magnetic field information to see how these factors are playing role. And these two have strikingly different star formation efficiency. One is, you can see here the hub filament complex. Here is the hub and this long tail like structure emerging out from this high massive star. And then for this particular case, I have looked at this simple like textbook like problem of 1157 separately, where it has a filamentary structure, class 0 protostar, and a starless core. So it's kind of a whole system which is all different kinds of initial stages of star formation going on. So I've looked at the magnetic field structure to compare the large scale envelope, to compare the large scale magnetic field to the sub-millimeter polarization, which is shown in this inset. So what was found out that within the uncertainty, the magnetic fields at the larger scale to the smaller AU scales, they are comparable, and the kind of magnetic fields, they are playing role in the dynamics of the cloud, and it is also preserved at both the scales. Moving on to the next section, these molecular line studies over these two complexes were studied, but I will be just discussing only one. As I mentioned, this is one of the classical example of hub filament morphology. So I've shown here, so I've characterized these filamentary structures by extracting them and calculating their physical properties by characterizing the radial profile structure. So these black lines are the extracted skeletons, and these white dots are the cores derived using astrodendrogram. And then I have shown one example in 12CO. This particular region is showing first time interaction of the high density structure, high velocity, low density gas, and the low velocity, high density structure around this massive stars. So that C18O molecular line, so basically the every pointing in the molecular line was characterized by the centroid velocity. And then I've looked at basically that how the velocity centroid, they are changing along the direction of this filament. So you can see before that the magnetic field is being dragged along this direction, and the gradient along this particular line is that I found out was 0.2 kilometer per second per parsec. So from my, sorry?
You have 2 minutes, please wind.
Okay. Okay, yeah. So from my calculations was found out that the dynamics is not following the scenario of a filament system as seen from the red shifted, as seen from the velocity gradient away from the hub. And these were the parameters that were calculated, and the virialized state of these cores were also characterized. So moving on to the next one. So this particular region also was studied in the Cephas flare region, where considering the case where the moving cloud is where the cloud is moving into the interstellar medium, it interacts with the magnetic field. So the shape of the shape of the molecular cloud is dependent on the offset of that direction of motion and the magnetic field structure. So basically, using the Gaia DR3 parallax and the Planck polarization map, I have done a kind of a comparative statistical study of the magnetic field structure and the direction of motion in these 4 clouds in the Cephas flare region. And what I found out by comparing different direction of motion and the magnetic field with the core orientation was that there was no preferred orientation, and the distribution was found out to be completely random, so which suggests that it depends on the local environment and the magnetized properties of each cloud. And the last part of my talk is related to this core orientation and magnetic field. So these so basically these set of molecular clouds, they are the isolated structures. They are steep radial density profiles, and in previous studies, it was found out that, so basically the point to catch here is that the morphology of all these isolated clouds is that there's a sharp kind of rim kind of structure on one side and the diffuse envelope on the other side. So the reasons given were the feedback from massive stars, or the anisotropic interstellar radiation field. So what I did was to find out the role of magnetic field in regulating the morphology of these cores and the embedded structures. So I've used the optical polarization aim-pole data and the Planck polarization maps to compare their magnetic field orientation with respect to the diffuse morphology. So what I found out that the magnetic field is along the direction of the extended emission of each cloud that you are seeing here in one of the case of L1512. And the core orientation with respect to the magnetic field were also found out to be random, that it could be depending on the local environment of each cloud. So with this, I summarize my work saying that, so with this thesis, I produced the first large-scale detailed kinematics of these 2 regions in Cephas flare, 1172 and 1147 at spatial grading of 20 arcsecond. So basically, this information of the large-scale molecular line studies, it is important in the understanding of filaments and the cores. And the magnetic field was also found out to be playing a crucial role in the dynamics. And we also found out the signatures of transonic and supersonic turbulence from the line width information. And from the motion information, I found out the macroscopic motions of the clouds are also important. And in addition to that, the distances in the direction of motion, as I said, they were also estimated, and various comparative studies, statistical studies of various orientations of the magnetic field with the motion and cores were also studied. And then the last case was related to that the magnetic fields, they are aligned. So definitely they are playing role in governing the morphology or shaping them to make in that particular form. So this work is an attempt to characterize the physical factors responsible for the evolution of these molecular clouds. And it paved a roadmap for to study larger sample of filamentary structures. So now the question comes that with these large scale molecular line studies, that how these magnetic field structures, they from the higher scales, they are related to the sub-parsec scales at higher density structures. So we need to look at the magnetic field structure at high resolution observations, and also like from the not be properly sampled. So for that we need higher spatial resolution observation using interferometry. So my future plans are related to study basically going more deep into the magnetic field structure and these molecular lines. So for these magnetic field structures, I have already started a work using JCMT to find out that how on the same cloud only, that how the magnetic fields are basically behaving in presence of the star at high density structures. So yeah, that was all from my side. Thank you. These are the publications.
Thank you, Ekta. So, Indulekha.
I just wanted to know about that velocity fields. You said they are not towards the hub, but towards a core which is not coincident with the hub. What about the density gradient in the whole structure? Could that hub be an apparent hub in the sense of overlap due to projection, and the core be actually sitting at the densities and peak?
Yeah, okay. Can you please repeat that?
You mentioned that the gas flow was not towards the hub, but rather towards that core.
Yes.
What about the density gradients which are present? And is that film hub an apparent hub in the sense of projection effects?
Yeah, you are right. So what we are looking in terms of the density gradient, if you look at, then this appears to be the massive, basically the point having higher gravitational potential. So this has the higher column density as we look into the Herschel column density maps. And this one is not having that greater mass, but when you look at the basically age of these two structures, so this particular region that is having intermediate mass star, that has already evolved. So it has actually cleared out the material away from the star. So it is not that completely concentrated that that will facilitate completely the motion of the gas towards the hub only. And like you said, for the projection effect, yes, I agree with that. The projection effect can also change the implication, but looking at the line of sight component of the velocity field, what I found out was that there is a positive gradient towards this core of 1172. So it is steeply increasing towards this direction as looking at the centroid velocity. So possibly that if you ignore projection effect, could be that the material is moving towards this as based on the gradient and the density structure.
Thank you.
Okay, so thank you very much, Ekta and judges. And we move to the last talk. Tridib, can you please unshare? Yeah, thanks. Tridib, we have your presentation here, so we can share it from here, and you can share when you want to go to the next slide.
Is your presentation?
Yes. This is my presentation. Okay. So how I'll move the slides actually? Yeah.
Tell me to change the slide and.
Okay.
Yep.
Yeah. So yeah, this my thesis talk is the pulsar radio emission and polarizations. Mostly I have done investigated to do some theoretical aspects. So my professor supervisor name is Professor Ati Gangadhara. I have done all those thesis works from Indian Institute of Astrophysics, Bangalore. So move to the next slide. Yeah. So pulsar paradigm is quite rich, and it was dated back in 1967 when Jocelyn Bell and Anthony Hui suddenly detected series of pulses while working in Cambridge radio antenna, and you can see the SPAPI signal which was recorded in a fast charter recorders. You can see this marked with CV199, and after pulsar discovery, it opened up a lot of diverse window. It opened a lot of window, and it's just a remarkable discovery because it opened several window like nuclear physics and GTR. So all those things can be studied by pulsar. So pulsar is no doubt it is one of the most important discovery. So next slide. Yeah. So pulsars actually pulsars generate very highly powerful radio beam from its magnetic axis, magnetic poles. So once its radio beam sweeps across our line of sight, we get a series of periodic signals, just like a lighthouse effects, and we call this lighthouse model. And you can see these references. Next slide. Yeah. So, so before going to the details, I just illuminate some basic details about the pulsar magnetosphere. So pulsar is a highly magnetized, highly gravitating spinning object, spinning compact object. So combined action of this spinning with this magnetic field lead to the extraction of the charged particles from the polar gap regions, because it generates huge electric field across the polar cap, that is around 10 to the power 12 volts. So once the charge is extracted, two things is happening. So because of the high ambient magnetic field, this perpendicular component momentum is easily it's getting dissipated away very quickly, and it is quickly reduced to the lowest Landau level. So you can see the electron zone, proton zones, and because of the depending upon the sense of rotations, the electrons and proton zone is generated in either side of the spin axis, and in between you can see the wind zone. So once it is reduces to the lowest Landau level, it is confined to the plane of the magnetic field lines, lead to the generation of the primary plasma, which is having Lorentz factor around 10 to the power 3 to 10 to the power 6. So that primary plasma generates curvature photons, and that curvature photons interact with the magnetic field, and via magnetic cascade process, it generates the secondary plasma. That secondary plasma is responsible for generating radio emission. So combined action of this rotation and all those things lead to the generation of the charge separated magnetosphere, which lead to the accumulation of the charge density. We call it as a Goldrich-Julian current density, and you can see the expression is given omega dot v by 2 pi c, and it is having implication. It is a very important parameter in pulsar astronomy. There have been speculated defined gaps in the pulsar astronomy, like outer gap models, polar cap model. Mostly I'll be talking about polar cap models, because polar caps the radio emission originating, and others gaps has been speculated to be to initiate X-ray and others process. Next slide. Yeah, so before going to the theoretical details, I'll be just talking about the observational insight. So how pulsars profiles is generated. Actually, there are polarization feeds in radio antenna. So once this raw voltage is detected and it is cross multiplied, and then it is after processing over several channels. So the individual pulses is generated. So you can see there is stacking. The individual pulses profile is stacked over different channel, and it is dispersed. It is then folded, and after integrating over 5,000 or more pulses, it generates average stable profiles. So in principle, individual pulses are highly variable and fluctuating in nature, but average pulses that is stable in nature. So it is plotted over the rotation phase, that is depicting the time evolution of the neutron stars. Next slide. Yeah. So pulsar radio beam is not a solid cone, rather it is a concentric. It is consist of core, and it is encompassed by hollow cylinder model. So central part is comprised of core, and it is encompassed by hollow cone models. That is called Rankine model, and it is phenomenological models. And the right side, you can see the 3D perception of these integrated pulse profiles. So depending upon the line of sight cutting trajectory, will encounter pulses. Once it is passing through the core region, we can will come up with 3 component profiles. One, once it is just gazing, it will miss the core and will come up with 2 component profile. And once it is passing through the outer rings zone, will be having only profiles. Yeah, next slide. Yeah. So there have been speculated, there have been proposed 2 types of model in the pulsar radio emission. One is it's claiming that pulsar beam is conal, and second type of model is claiming this pulsar emission is patchy. So most of the observations support Rankine's model, but the second model is claiming that the emission component is arbitrarily distributed across the emission zone, and depending upon the number of components present along a line of sight, it will contribute accordingly. But most of the observations support Rankine's model that I have earlier told. That's core and conal component, just like a hollow cylinder core model, and that is most of the observer assume that model and initiate their speculations. Next slide. Yeah, so we have theoretically generated polar caps boundary actually just by invoking the condition that curvature vector is perpendicular to the spin axis at the surface of the light cylinder. We have generated polar cap boundary. You can see that left panel is corresponding alpha is equal to 30 degree. Alpha is the magnetic axis inclination angle, and it is having range, y-axis dimension is having range within plus minus 145 meters, and in the x dimension it is having range plus minus 138. And as I move to the higher inclination angle, alpha is equal to 80 degree, you can see highly asymmetric type of profile. This x dimension is getting squeezed because once it is highly inclined, then more number of open field line will be closed actually. So as a result, this boundary will be shifted or squeezed. And the emission will also be, it will in terms limit the emission also. Next slide. Yeah, so pulsar, most of the emission model assume that pulsars magnetic field topology is predominantly in dipolars. So at least in the emission radio emission zone, so we have generated dipolar magnetic field line with a step of phi is equal to 30 degrees azimuth, magnetic azimuth, and we have generated the dipolar magnetic field line. Now, as pulsar radio emission is highly relativistic, so it is coming in the form of a cone, very narrow cone. It is coming from a transversely compressed zone, which is having angular width 1 by gamma. Gamma is the Lorentz factors, so it is coming from a very highly transversely compressed zone. And once we map this angular zone into the theta phi plane, theta is the colatitude and pi is the magnetic azimuth, then we'll generate emission zone as I have shown in the green contour colors. So for each magnetic field lines, there existing one emission zone, and on the right side you can see the emission zone is distributed across the whole pulse range. So once you zoom, the red color contour is showing the distribution of all the emission zone across the whole magnetic phase. So once you zoom the red color contour, then we'll see the left side that is having some span in the theta phi plane. In the center of this emission zone, magnetic field and line of sight and magnetic axis exactly aligned, and at the boundary it is subtending an angle 1 by gamma. Next slide. Yeah. So we have by solving this curvature radiation mechanisms and taking the Fourier transformation and solving the timing integral, we have computed the Stokes parameter in terms of modified Bessel function. And then once it is done, we have to integrate over the whole emission regions numerically. Then it will be comparable to the observed one. So once it is done, then we have to compute all the Stokes parameter over all the emission grids numerically. Then we'll be generating the simulated pulse profile. So
if you have 2 minutes, you have 2 minutes.
Okay. Yeah, sizing the main result. Yeah, so these all are showing the simulated pulse profile, and it is overlaid with these modulation functions. Once there is a non-uniform plasma distribution, you can see the anti-symmetric type of circular polarization, and for negative impact factor, and you'll see that the polarization angle curve is getting reversed. Next slide, please. Yeah, so if you don't use any modulation function, you'll see this circular polarization get vanished, because it is in either side of these emission regions, there will be equal number of electric field vector oriented in upward and positive direction and negative direction. So it will cancel out, and as a result, we'll see the negative vanished circular polarizations. Next slide. The same things we have generated multiple component we have generated pulsars, and in the caption we have mentioned all the details, and for the details loops you can see my papers. Yeah. Next slide. Yeah, so I'll be just talking about this coherent and incoherent. That is my actual contributions. So coherent radiation, actually it will be the way it will be correlated in space, and as a result we'll be getting enhanced radio emissions. So my contribution is to add the plasma bunch topology and generate the simulated pulse profile. So I have shown the expression of this electric field, Fourier component of this electric field. So you can see there is a sign factor which is called the selection factor. So once this emitted wave number is resonantly matching with this Langmuir modes, then it will perfectly coupled and it will generate the enhanced emission. If it is not perfectly coupled or perfect resonance condition is not satisfied, then the emission will go down. So that is my contribution actually, which you have tried to portray. For details, you can have a look in my paper. Please, next slide. So this is the geometry. So you can see this plasma bunch is coupled or embedded in the dipolar magnetic field lines, and this mu is the angle between the line of sight and the field of the magnetic field lines. Once all this formulation is done in the plasma frame, then we have converted it back to the neutron star centered frame. Then we have generated the simulated pulse profile. Next slide.
Can you please move to conclusions?
Yeah. So
time is up.
Yeah, just last slides I'll be talking. So I have generated these simulated pulse profiles. So we can see on an average, it is simulated symmetric types of pulse profiles. So the same things continuation of the same work. Please move to the last next slides. Yeah, the same 3-component profile we have generated. And once it is done, then we have computed the brightness temperature solely from these theoretical frameworks. Then we have compared with the observed ones, and we have found that we have rough agreement with this observations one. That is corresponding to 10^25 Kelvin temperatures, and so on. So, yeah, the main contribution is that we have included the plasma bunch topology, we have solved the emission beam geometry, and we have generated the simulated pulse profile based on the coherent curvature radiation models, and we have achieved brightness temperature purely from the theoretical basis, which is having rough agreement with this observed one. Maybe I'll end up here.
Okay, thank you very much.
This is my future implications. Yeah, so it is related to the fast radio burst model. So I have shown if there is some plasma ramp pressure, so there is some perturbation like AGN outflow, which can perturb this magnetic field. Eventually, if it is having the ramp pressure exceeding 10^8, then it can distort the magnetic field, and eventually it will lead to the rapid oscillation of the column. So along with the stringent magnetic field and rapid oscillation eventually can experience the fast radio burst type of temperatures.
Okay, so, I think we will move to questions since we are already running behind schedule. BCJ?
Yeah, so I had several questions, but I think I'll ask the 2 most basic questions. So can you answer in just 2 or 3 sentences, what was the motivation of doing this geometric modeling which you were presenting? And the second thing is, we know that retardation and aberration affects the pulse profile shapes, they become asymmetric. I didn't see in any of your slides any discussion of that. So can you answer the 2 questions shortly, very short?
Yeah, so basically if you need to in order to produce the simulated pulse profile, you have to solve the geometry. So by invoking all those line of sight geometry and condition, we have estimated these emission coordinates. Once it is done, then you'll be able to produce the simulated pulse profile. So geometry is basically very important to probe these pulse profile structures, yeah. So and it will eventually explain all those diverse property actually. All are related to the polarization business or polarization stuff. Yeah, and second question I'm coming up. Your question is
so are you claiming that purely by this geometrical thing you will be able to explain the extremely rich diversity of the single pulse phenomena? Is that what you are claiming?
No, I'm not claiming, but you have to add perturbations along with all those geometry. Then you'll be able to explain these asymmetric type of profiles and all other diverse things. But yeah, there are a lot of things you can't explain, like orthogonal polarization mode phenomena and all those things you can't explain. But this is but you have to solve the geometry, then you'll be able to produce the simulated pulse profile theoretically.
Okay. What about retardation, aberration, and the symmetry in your simulated profiles?
Here, aberrations, there is finite rotations. Once there is finite rotation incorporated in the profile in the model, then you'll see that this tangent vector will no longer be aligned with your line of sight. So that do have some implications to change the pulse profile structure. Actually, it can eventually generate asymmetric type of profiles. Retardation is defined emission component is coming from the defined path. As a result, it will induce extra propagation delay. So once the extra propagation delay is added, it will automatically get squeezed. If you analyze the multiple component profile, you'll see this conal components getting squeezed with respect to the core component. So that has been already explained in the pulsar literatures, like Gangadhara and other things. They have done all these models. Yeah.
So if BCJ, can we, does that answer?
Yeah. No, I'm through. Okay.
Okay. Thank you very much. And to all the presenters, we have come to the end of the session. Thank you also to the judges and all the audience. So we are dispersing for tea now here in person.
Yeah.
We will be meeting.
Just one announcement.
Okay.